So we're going to talk about what are called Fermi estimations. Today is 9/16/21. What does it mean to estimate something? Don't you dare say take a guess. I hate the language that we use early on. Well, it means to try to make an approximation. Yes, that is a great word to use here. It's an approximation of the true value of something. So if I ask you, how many cups of coffee did you have this morning? Or how many ounces of coffee did you have this morning? Or maybe you don't drink coffee because, well, I don't know what you people do who don't drink coffee. But anyway, you might not know exactly how many ounces you drank, but you can probably, I don't know, 3 cups, maybe they're 10 ounces, somewhere around 30 ounces of coffee. Okay. That's an estimation. You're basing it on something. Those numbers are not coming out of thin air. It's based on something. So we know that we're going to be making an approximation of some kind of values that is based on some numerical input. What the heck is an order of magnitude? It's a power of 10. So if I had to ask you to estimate to the nearest power of 10 how many pairs of shoes you have at home, I would guess that for most of you it's order of magnitude 10 to the first. You have, more than one pair, probably. Most people in this country have more than one pair of shoes. You probably have less than 100. Every now and then I run into somebody who's like, oh no, 10 to the second. But they're real outliers. So order of magnitude is the power of 10. So an order of magnitude estimation is us taking some knowledge, some information, and estimating to the nearest power of 10 how many of something there are. What power of 10 is closest to the true value of the number in the expression? What power of 10 is closest to the true value of the correct answer? That's going to make more sense in a second, and we're going to do some of these. We use Fermi estimates, and I always get really happy later in the year when I can actually use a Fermi estimate for something, and I go, look, we can Fermi it! And all the physics students go, ugh. And, I dance around like a crazy person, but that's okay. What a Fermi estimate does for you is it gives you a reasonable estimate of the answer. So if you've done all your calculations to, the thousandth of a gram and the thousandth of a newton, but you don't know if something was wrong in the calculations, you can do a very fast ballpark estimation that should give you an idea of whether or not you're just in the right ballpark. So if the final answer that you came up with for something was, let's see, 5.6 times 10 to the 7, well, here, no, let's make it really, really stupidly detailed. Let's say you came up with 5654928.333 newtons as your final answer. You did a whole page of calculations, pages of calculations, hours of work, sweat and blood and tears. And you get this number and you have no idea if it's right, but you do a quick Fermi estimate. And the Fermi estimate with almost no math says that your order of magnitude for your should probably be about 10 to the 7th. You look back at this answer and go, let's see, 1, 2, 3, 4, 5, 6. Okay. Order of magnitude estimation gets me pretty close. This is not an unreasonable answer. If you do an order of magnitude estimation and it comes up and says, yeah, your answer should be somewhere around 10 to the 3rd, something has gone horribly wrong. So they're a very fast check. Dimensional analysis is a way to basically check that you rearranged something correctly, to check your algebra. This is a way to check your calculations. So we're going to watch this cute little video on Fermi. Hold on. Number 4. We'll look. Okay, so we've got some problems here that were assigned on Fermi's, and as I mentioned, we're going to actually do these together because they are kind of unwieldy. So starting with number 36, and I've got the screenshot here. This is the number of table tennis balls, that would be ping pong balls for us mere mortals, that fit without being crushed into a room that's 4 meters long, 4 meters wide, and 3 meters high. We're given an assumed diameter of the ball. So let's talk about specificity, shall we? What does specificity mean? How specific you're going to get. There is Fermi purism. Notice that in that video, they're literally only using powers of 10. So think about a number in scientific notation. They're literally using no coefficient. They're not saying 5 times 10 to the third. They're just saying 10 to the third. So if we want to be, the funny thing is that with Fermi's, the most correct way to do it is probably the least specific. Because we literally want to come up with just an order of a power of 10. So I find it helpful when I'm doing a Fermi to think in terms of the large picture here. So the number of ping pong balls that are going to fit. Obviously, it's related to volume, right? So number of, we'll say PP balls, ping pong balls, table tennis balls, whatever, is going to equal some relationship between the volume of the room and the volume of the ball. Yes? Well, there are 2 options. What are they? Volume of the ball divided by volume of the room, or vice versa? What do you think, Davey? Okay, so remember how I said we use a whole lot of subscripts in physics? Now, obviously, we can't use the letter V because that typically stands for velocity, so I am going to use VOL. So we have VOL sub room divided by VOL sub ball. So if we want to do a fast order of magnitude estimation for the volume of the room, we're given exact measurements. We could actually put 4 times 4 times 3. Or we could say 10 to the 1 times 10 to the 1 times 10 to the 1, 10 to the third. Order of magnitude. So, I mean, that's really sloppy. 10 to the third cubic meters. What's the actual answer? 16 times 3, 48. So that's pretty far off. That's a huge overestimation. Well, so we have the diameter of a ball. This is where people get in trouble. Because my smart mathy people always want to do, well, pi 3/4 pi r cubed. That's the volume of a sphere. It is, but this is a Fermi. So we have, for the ping pong ball, if we estimate this as a cube rather than a circle for one thing, because they're not going to, they're not going to nest. It's basically order of magnitude 10 to the negative second per side. So 10 to the negative second cubed. So here we have 10 to the third. This would be 10 to the negative sixth. What would our answer be then? Well, we'd be saying that we think we could get 10 to the 9th ping pong balls in there. That's what, 1 billion ping pong balls. It's a lot of ping pong balls. Let's see how different an answer we get if we are so, okay, this is what I'm going to say. Pure Fermis rely on only powers of 10, only orders of magnitude. If we want to do a little better than that, 4 times 4 times 3, okay, that's 48. I could say, so, this is the purist's approach. I'll call this the fudgy middle ground. I tend to go to the fudgy middle ground myself. So I'm going to keep this part because I still believe that this is correct. That volume of the room divided by volume of the ball is going to give me my answer. And I'm going to bring this over here. But what if I get a slightly more specific answer? So if I say 4 times 10 to the first cubic meters is my volume of the room, which I struggle with the fact that I put a 4 out there. Actually, you know what? Hold on. Back off a second. Back off, Moser. 48, so I'm going to say 10 to the second for that. Sorry. This is the fudgy middle ground. We'll do one more that's the nitpickiest or nitpickier. So I'm still going to use that estimation of the ball as a cube, but I'm going to say that, 4 times 10 to the negative second cubed, well, 4 times 4 times 4, I've got 64, so I'm up to 64 times 10 to the, okay, you don't know how I did that, and I should back up, because I see the crinkly brow. That's good. I like the nonverbal. That's useful. What did I just do in my head? Here's what I did. Here's my approximated ping pong ball. Each one of these sides is 3.8 centimeters. If I kind of round that, I could say that's 4 times 10 to the negative second meters. Okay, so 4 times 4 times 4, because this cubed would be the volume. So 4 times 4 times 4, 16, 64. So I would have 64 times 10 to the 6th, which isn't correct scientific notation. I'm aware of that. It's okay. For an intermediate step, we can get away with that, not for a final answer. So what if I just then, because that would actually, oh, I'm so terrible at this, times 10 to the, oh, negative. Try negative there, Moser. So then that would be 6.4 times 10 to the negative 5th. 6.4 times 10 to the negative 5th. So I'm going to say that this is just 10 to the negative 5th meters cubed. So what does that get me? Well, that gets me a number of ping pong balls of 10 to the negative 7th. Or I'm sorry, 10 to the 7th. Good God. So it's different. It's significantly different. This is what, the smaller the numbers are, the harder it is to use the purest approach. The purest approach works better with larger numbers. So what if I'm a real pain in the tuchus and I want to say, well, I have, 48, let's say 5 times 10 to the first cubic meters is the volume of the room. Equals volume room. Well, I had 6.4 times 10 to the negative 5th meters is the volume of the ball. I could actually get a reasonable number this way. So 5 divided by 6, I need a calculator. Oops, I forgot to unpause that. So, students hate these because there are 3 different answers and which one's right, and the fudgy middle ground is generally the good middle path to shoot between a number that's really pretty far off and one that took so much time you might as well have done the whole problem. Okay, number 33. You are the equipment manager of a professional baseball team. One of your jobs is to keep a supply of balls for games in your home ballpark. Balls are sometimes lost when players hit them into the stands as home runs or foul balls. How many baseballs do you have to buy per season to make up for such losses? Assume that your team plays a 81-game home schedule. Okay, so number of baseballs needed equals number of, well, basically we could cross out the number that are lost. So what factors do we know? We know how many games we have Do we know how many balls are lost each game, or can we make a reasonable estimation? Do you think, and this is where the broadest powers of 10. So basically, number of games times number of baseballs lost per game. So we have this. This is what we need. And when we use the broadest Fermi estimation possible, do you think it's 1? Do you think it's 10? Or do you think it's 100? 1 seems unreasonable to me. I think that's unreasonably low, and I know nothing about baseball. Like I said, I'm there for the snacks. 100 seems unreasonably high to me, which leaves us with a middle ground of 10. So if we say that this is order of magnitude 10 to the second, because 81 is closest to 100, and we say that this is order of magnitude 10 to the first, then we would estimate that we need about 1,000 balls a season for replacement. Here's the deal with Fermis. They are fuzzy. The thing that you have to do to get credit for a Fermi is to show your assumptions. So I'm going to give you one. Yeah. Let's do this. So, well, actually, we'll do one more together, because I promised you we would do these all together. 29, is it? So not on there. Nope, not there either. There she is. Ooh, estimate the number of breaths taken during 70 years, the average lifespan of a person. This is a good one. I like this one. So, number of breaths would equal, well, breaths. So here's one where I get to make my point about this. You can't pull a number out of thin air. So do you feel like you can get a reasonable estimate on how many breaths somebody takes in a day? No. But do you think you could get a reasonable estimate on how many breaths you take in a minute? Okay, I just took a nice deep breath, and I think it took me longer than a second, or close to a second. So maybe I take 30 breaths a minute then. So if I take, whether I take 30 or 60, the order of magnitude is it closer to 10 breaths a minute or 100 breaths a minute? I think it's closer to 10. I think 100 breaths a minute and you'd be passed out under something with breathing in a paper bag because you would have hyperventilated. So if we look at breaths per minute times minutes per day, hey, look at that. It's dimensional analysis. It's factor label. Oh my God, look at that. The units work. Sometimes you can do that with Fermis. Breaths per minute times minutes per day gives you breaths per day. Handy little trick. Okay, so we think that the order of magnitude of breaths per minute is 10 to the first. Well, how many minutes per day? Well, let's see. 10 to the first, and this is again where we can get real specific or not. So 60 times 24, 60 minutes in an hour, 24 hours in a day, which would be, what, 120, 1200 roughly? Yep, 1200 roughly. So I'm going to call that 10 to the third. Because I don't want a specific number. I don't care about the specific numbers. I want a very broad estimation. So that gives me breaths per day of about 10 to the fourth. Can I prove this? Maybe. Could I look it up? Yeah, probably. But the big thing is then if I'm doing a more detailed calculation, I have this to look at and go, yeah, it's in the right ballpark. I think that's probably pretty close. How much do you hate them so far? Okay, which of the following is the best order of magnitude estimate in meters of the height of a mountain? So, Americans have a hard time thinking in metric. This is a meter. Rogers is about 10 kilometers away, roughly. So that would be 10,000 meters. Do you think that a good order of estimation for the height of a mountain is one of these, 10 of these, 100 of these, or 1,000 of these? Yeah, probably 1,000. So, in the U.S., we measure elevation and altitude, of course, in feet, and a meter is just over 3 feet. So, a 1,000-meter mountain is about a 3,500 foot mountain. That's an actual mountain. Okay, questions, comments. You're going to get credit just for turning these in. Here's what we're going to do tomorrow. Oh, this will be so much fun. You're going to have a mixed FIP. So, wait, hold on. Tomorrow when you walk in, we're going to have a FIP over 5 and 6. Normally the way I work this is this homework is due before this FIP. I kind of screwed up and we didn't do a separate FIP on DAs. Actually, you know what? That probably should just be one FIP. So you'll have a FIP tomorrow and we'll go from there. I actually love the forgot to resume. So tomorrow when you walk in, 5D and 6D FIP, all of this homework should be turned in then, because you want it done before the FIP, not after. And the video that's linked in the practice, the bonus video with the mild language warning, is awesome. We'll watch it in here because we have a few minutes. So, questions? Shout. Everybody hates Fermis. I know. It's okay.